The physical world generates information in a raw, chaotic state. Machine learning algorithms, however, process pure numerical values. They have no intrinsic understanding of what those numbers represent in reality. Governments, central banks, and researchers attempt to capture this reality by running massive economic and household surveys. The result is millions of rows of multivariable data, tracking everything from a population's age to their annual income. Predictive algorithms process the raw magnitude of these numbers, completely blind to their physical units. A machine learning model does not know what a year is or what a dollar is. This 3D scatter plot compares human age against salary. Geometrically, the data stretches massively along the vertical axis. Because algorithms only read numbers, they weigh salary thousands of times higher. The regression line violently snaps parallel to the salary dimension, effectively breaking the model. Before any machine learning begins, the raw inputs must be geometrically sculpted, filtered, and standardized to remove the bias of human units. Exploratory data analysis, or EDA, is the mathematical process of investigating datasets to summarize their structural geometry. It provides the essential pipeline that transforms chaotic records into actionable, scale-invariant vector spaces. The first step in this pipeline is defining the central tendency of a one-dimensional array. We have to find the anchor point of the data. This animated diagram displays a clean, continuous dataset using a simple ordinal array of integers, 1 through 6. To find the mathematical average, we calculate the mean. The mean is a measure of central tendency, calculated by dividing the sum of all values by the total number of values. Here, the mean acts as a physical fulcrum, perfectly balancing the weight of the array. Now watch what happens when a severe outlier enters the dataset. The mean is highly sensitive to magnitude. A single extreme value drags the fulcrum 4 to the right to maintain mathematical balance, completely misrepresenting where the vast majority of the actual data lives. To counter this, data scientists use the median. The median is the value separating the higher half from the lower half of a data sample, strictly identifying the spatial, indexical center of the array. It ignores magnitude entirely. This makes the median a statistically robust metric, meaning it retains its predictive accuracy even when the data is contaminated with extreme noise. The mean is computationally efficient for perfectly clean data, but the median provides the geometric anchor required to protect real-world models from severe anomalies. Once the center is anchored, the next step is quantifying how far the data spreads across the vector space. This visual maps variance. Variance is a measurement of the average squared distance of every single data point from the mean of the distribution. When calculating variance from a sample rather than an entire population, we use Bessel's correction. Bessel's correction is the practice of dividing by n-1 instead of just n to correct a known mathematical bias that underestimates population spread. By taking the square root of that variance, we get the standard deviation, which simply returns the metric back to its original, readable units. The box plot serves as a programmatic logic gate, moving beyond simple visualization to actively isolate and cull noise from the signal. The dataset is sliced into percentiles. The boundaries of the central box are drawn exactly at quartile 1, the 25th percentile, and quartile 3, the 75th percentile. The distance between these two walls is the interquartile range. The interquartile range, or IQR, is a measure of statistical dispersion calculated by subtracting quartile 1 from quartile 3. It represents the exact middle 50. The logic gate is now active. Any single data point falling beyond these mathematical fences is classified as noise and deleted from the array. The interquartile range provides the rigid mathematical fences perfectly required to computationally isolate the truth from the noise. Once the extreme noise is systematically purged, continuous real-world variables reveal a predictable geometric shape. Take biometric measurements, like the physical dimensions of the iris flower petals. This animated histogram demonstrates how the clean data points stack based on frequency. The vast majority of the biological samples cluster heavily around the median. We overlay this with a probability density function. A probability density function is a statistical expression that defines the likelihood of a continuous random variable taking on a specific value, creating a smooth bell curve over the data. This shape obeys strict volumetric laws known as the empirical rule. The empirical rule is a statistical guideline stating that for a normal distribution, almost all observed data falls within 3 standard deviations of the mean. Exactly 68% of the data volume lives within the first standard deviation from the center. Expanding outward, 95% of the data falls within 2 standard deviations, and 99.7% falls within 3. We see this geometry in complex human environments too, like the consistency of athletic scoring over a cricket season. A narrow bell curve indicates highly consistent, predictable performance, while a wide curve represents higher volatility and a massive variance in outcomes. Proving that data follows this Gaussian distribution is the prerequisite for predictive modeling. It allows data scientists to map the precise frequency of an event simply by measuring its geometric volume. We now have clean bell curves, but we face the problem established in Act 1. The variables exist on completely incompatible scales. This graphic illustrates the distance between our 2 datasets. The age curve centers around 30, while the salary curve sits thousands of units away at 60,000. To fix this, we use the z-score equation. A z-score is a statistical measurement that describes a value's relationship to the mean of a group of values, expressed strictly in terms of standard deviations. Subtracting the dataset's mean from every individual data point forces every curve, regardless of its original value, to slide along the axis and center perfectly at 0. Then we process the denominator. Dividing those points by the standard deviation forces the variance of the 2 curves to match identically. The 2 disparate variables merge into a single mathematical object, the standard normal distribution. The standard normal distribution is a curve where the mean is exactly 0 and the standard deviation is exactly 1. Standardization effectively deletes physical units, transforming incompatible variables into a single, scale-invariant vector space that algorithms can process fairly. The final stage of the pipeline converts geometric distance into literal probability. This diagram shows the standard normal curve being evaluated using a z-table. A z-table is a mathematical chart used to calculate the exact area under a specific slice of a standard normal curve. By taking our calculated z-score to this lookup table, we find a precise decimal coordinate correlating directly to the highlighted area. That decimal translates directly to a percentage. The algorithm now knows there is exactly an 89.44% probability of an event occurring below that specific threshold. This transition from raw metrics to pure probability limits forms the bedrock of all inferential statistics and machine learning classification. Chaotic, unreadable reality is systematically cleaned, mathematically fenced, and standardized, becoming the pure geometric fuel required for artificial intelligence.